Hi everyone. So today we're going to talk about some applications of Cauchy's theorem and formula to computing real integrals. This is cool because Cauchy apparently his first paper that he wrote on complex variables had to do with using complex numbers to evaluate some real integrals. So this goes back to, in a way, in spirit, goes back to the roots of this whole subject. At least it's more modern development proceeding from Cauchy's contributions. So anyway, so before we get down to business, I'll just remind you of some things we talked about in the last lecture on Cauchy's theorem and Cauchy's integral formula. So Cauchy's theorem, you'll recall, says that if you integrate a holomorphic function around, basically it says if you integrate a holomorphic function around a closed curve, you get 0. And so to be really precise about that, gamma is a typical curve. So typical means that it's closed, it's piecewise smooth, and it's oriented counterclockwise, and it is a simple curve, so it doesn't self-intersect. And also we're assuming the interior of this curve lies within a domain where f is holomorphic. Okay, so everything inside the curve, f is defined in holomorphic there. And just a reminder, holomorphic means that that f is analytic, so f prime exists at every point in this domain, and also that f prime is continuous. So in other words, f has continuous partials. Okay, so another way to say f is holomorphic is that the partials satisfy the Cauchy-Riemann equations and they're continuous. Okay, so that's Cauchy's theorem. So basically, if you're in a domain of where f is holomorphic, you integrate around a closed curve and you get 0. Okay. Now Cauchy's integral formula tells us that the values of a holomorphic function in a domain where f is holomorphic are determined basically by any curve that surrounds that point. So if you draw any curve, gamma, any closed curve gamma, and the function's holomorphic inside of there, the values of the function on gamma determine the values of the function at any point inside that curve by this formula. So we have f of z is equal to 1 over 2 pi I times the integral around gamma of f of zeta over zeta minus z d zeta. Okay, so we have this rational function of z, and we're integrating that with respect to zeta, and that gives us the value of our function at z. Okay, so just to be clear, this formula holds when your gamma is a typical curve. Again, all those adjectives: closed, simple, piecewise smooth, oriented counterclockwise. And that typical curve, the interior of that z is going to be contained in that interior, so this curve is surrounding z, going around z, and 2, that whole interior is contained in a domain where f is holomorphic. Okay, so f has to be holomorphic throughout the interior of that curve gamma. All right, so those were the theorems that we covered last time. Okay, and well, actually, we'll start by using Cauchy's integral formula. So let's, maybe I'll leave that up here for the moment. I'll only need Cauchy's integral formula to begin with, so I'll just put that up there. Okay, so here's an example where we're going to apply Cauchy's integral formula to compute a real integral. So we're going to consider the following integral. Okay, so considering this integral, and this is not, at least as far as I can tell, doesn't seem like the familiar type of thing that you would see in Calc 2, that you would learn how to integrate by some standard method in Calc 2. So I don't know, maybe there's something clever you can do that a Calc 2 student would do, but here's something clever we can do because we know complex numbers. So basically what we're going to do here is to start off our calculation of this, really the key thing is going to be, so basically this integral here, we're going to think about this, so the way we're coming at this is we're going to hope that this is the integral, that this is a complex line integral in some parameterization. And because the thetas are here and we have 0 to 2 pi, it's kind of natural to think that maybe this parameterization is going around a circle, maybe the unit circle. And we'll see that that really is the case. And the key to seeing that that's the case is to just use the definition of sine theta in terms of complex numbers. So we know our definition of sine theta is the following. Right, so we just substitute in the definition in terms of the complex exponentials. Okay, and to clean this up a bit, so I can multiply top and bottom by 2i. So I can multiply by 2i over 2i to take care of that annoying little fraction there. And also a key maneuver here is we're going to multiply by e to the I theta. Because that e to the minus I theta is really 1 over e to the I theta. So again, it's like a fraction, and it'll just be more seemly looking if we get rid of that fraction. Okay, so if we do that, what do we see? Okay, so we have the 2i e to the I theta d theta. And we have, let's see, we have e to the I theta squared. Right, that's coming from this this middle term here, so this guy right there. And then we have 4i e to the I theta. And that's coming from when we multiply through with that term. And then this last one here, so that's our second term there. And then our third term is when we multiply on this guy here. And what we find is we just have a minus 1, right? Okay. And now, as I said, we want to think about this sort of backwards. So we want to think about this as a complex line integral that we've parameterized over an interval, right? So our variable here is going to be theta, and that's going to be in the interval from 0 to 2 pi. Right, and what we can notice is if we let this be our z, right, so z of theta, instead of z of t, I usually parameterize with t, but here our natural variable of parameterization is theta. It doesn't matter what you call it, right? T, theta, doesn't matter. So if we were to make that e to the I theta, then dz d theta, right? Usually we have to compute dz dt and multiply that when we're computing a complex line integral. So we'd have I e to the I theta, right? And that's right here. So maybe I should, yeah, anyway, I guess I don't need another color. Okay, so that's right there. So we have our z and we have our dz d theta. So what I can say is that this is the integral. So it's going to be over some path here, and what we have is the function. So we have 2 over z squared, right? So my e to the I theta, that's z, plus 4I times z minus 1, and then times dz. Because that dz, remember, so this is our f of z here. That's f of z. And then when we compute a complex line integral, our dz, that reminds us we have to insert the dz dt times dt, right? But that's exactly what we have here, our I e to the I theta. That's our dz d theta, and then d theta. So this really, so if you go from here right to left, that would be how you write the complex line integral in terms of its parameterization. So we just went backwards here by just sort of guessing correctly. Well, by just making a natural, educated guess about what the most natural parameterization would be. And so we see here the curve gamma that we're going around. We can deduce that from our choice for z. So z is e to the I theta, theta going from 0 to 2 pi. This is just the counterclockwise parametrized unit circle. Right, so this gamma, I guess I can write it, yes, you can write that gamma. It's the set of z such that the norm of z is equal to 1. Okay, so we'll just write the integral that way instead of writing the generic gamma. All right. Make sure I'm on track here. Okay. So, usually when we compute a complex line integral, we parameterize it and then we do the real integral, right? But here we started with sort of a real integral, but that's clearly not the way we're going to compute this, because we started with the parameterization, the natural parameterization, and we got an integral that we didn't immediately recognize how to do using the usual tricks. So what we're going to do is we're going to try to apply Cauchy's integral formula. Okay, so I want to identify, well, so basically I want to take this integral here and I want to realize it in the form up here. Okay, so I want to look at, so I want to be looking at this integral here, in particular the inside of this integral, right? So in particular this integrand here. Right, so I want to be integrating this kind of, well, I'll allow anything in the numerator, but then I have to have a kind of linear type expression in the denominator. And down here in the denominator, what I have is a quadratic expression. Okay, and so basically, well, to go from quadratic to linear, we're going to want to factor this thing. All right, so the basic thing we want to do now is to use Cauchy's integral formula So we're going to factor this thing into z minus p times z minus q, right? And then, well, it'll depend on, we'll have to look at the details to decide whether we're going to choose p or q, but then basically our f is going to be, well, up to some multiple is going to be 1 over z minus q, say, and then the z minus p, that's going to be this analog of zeta minus z up there in Cauchy's integral formula. Okay, so that's the basic plan, is we'll sort of split this integrand up into two pieces, and one of them is going to be that sort of rational function denominator in Cauchy's integral formula, and then the top is just going to be sort of whatever is left over. Okay, so that's the plan, so you sort of see where I'm going with this, and then I'll show you the details here. So to continue with this idea of factoring, so we have this quadratic, the factors are just going to be the zeros of this quadratic, right? So these p and q, we find that those are exactly the places where this quadratic is equal to 0. So if we set z squared plus 4i z minus 1 equal to 0, quadratic formula applies, and we can say that z is negative the b coefficient there, plus or minus the square root of b squared. So let's see, that's negative 16, right, because of the I there. And then minus 4ac, that's plus 4. And then divide by 2. Okay, and that's negative 2i. And then we have what here? We have negative 12, square root of that, we're going to get 12 is 4 times 3. So square root of 4 is going to be 2, but that'll cancel with that 2 in the denominator. And then we'll have the 3, the negative, it'll be a negative 3. So what we're really going to have is a plus or minus, square root of negative 1 is I, and then we have the square root of 3. Okay, so this is I times negative 2 plus or minus square root of 3. Okay, so those are our two roots. And let me make some more room for myself here. All right, I'll refer back to Cauchy's integral formula in a second. Okay, so here's where we have to take a look at our curve here. So, or well, let's just take a look at where these points are, because that's going to be relevant, where the points are located. Because remember in Cauchy's integral formula, important clause is the curve whose interior contains z, right? So that's this z here. Okay, so we need to make sure that z that's going to be in the denominator, which is going to be either p or q down here, we need to make sure that's in the interior of our curve. So our curve is the unit circle, so we need to know where these 2 points are relative to the unit circle. So there's our unit circle, and our 2 points, well, one of them is at, we have, so there's like negative I, negative 2i, and then even further down here somewhere is going to be I times, gosh, I should probably, hold on a second. Yeah, let's write it this way. Negative I times, I times negative 2 minus root 3. Right, that's going to be at like negative 3.7 or something, roughly, negative 3.7 I. So that's way down here outside the circle, right? But if we look at I times negative 2 plus root 3, well, root 3 is like 1.7 roughly, so that's going to jump up into like right around there, right? So let's see, so we'll have, so this can be our Q down here, but our P will be squarely inside the unit circle. Okay, so that P, that's gonna play the role of Z in Cauchy's integral formula up there. Okay, so let's see here. So we know what P and Q, so I'll just be explicit about this. So our P, we're defining P as as I times negative 2 plus root 3, and Q as I times negative 2 minus root 3. Okay, and so we can continue with our integral computation. Okay, so that's going to be right here. It's the integral around, oh, and then I'll fix it up so I have the 1 over 2 pi I as well. So 1 over 2 pi I, the integral around the unit circle, 4 pi I. Okay, so I'll do this, I'll make sure this is clear. So Z minus P times Z minus Q dz. and that is equal to, and here's where so this is the last little algebra step here. We're going to put this z minus p, that's going to be like the rational function part with the zeta minus z in the denominator of Cauchy's formula. So we're going to have 4 pi I over z minus q. This is our f. This is f of z. Okay, so our variable of integration down here in our computation we're doing is z. In Cauchy's integral formula, the variable of integration is zeta. So you just have to disambiguate there for yourself. Okay, so down here we have variable integration is z, up there it's zeta. Down here we have p, up there it's z. Okay, so p down here is playing the role that z does up there, and then this is dz. Okay, and then so Cauchy's integral formula tells us that this integral, because so first we have to check here that this f is a holomorphic function in this domain which is inside of our curve gamma. And it is, because the only place that this function has trouble existing and might have trouble with its derivatives is at the point Q, but that's well outside the circle. And so this function is defined in holomorphic. It's a rational function, so no problem there. And our curve is a typical curve. You know, it's a smooth curve. It's closed. We're going counterclockwise. Simple, and right, and yeah, the interior of it is contained in a domain where our f is holomorphic. So we're perfectly within our rights to apply Cauchy's integral formula, and what we find is that this is that f evaluated at p, right? Because up there, right, the z there, that corresponds to the f of z on the left-hand side, right, in this formula. I'm looking right here. Whoops, whoopsie daisy. Okay, so that means we have to plug in this thing here. That's what goes into the function. Okay, and so what is that? That's 4 pi I over, so we're plugging p in, so we're going to get p minus q, right? And we look at our p and we look at our q, and we have a minus 2i in common, so that's going to cancel out when we subtract. And then what else is going to happen? We have I times root 3, then plus another I times root 3, right? Double negatives. And so we have 2 root 3 times I. Okay, and then we can clean that up just a little bit. Just cancel some stuff. The I is in a factor of 2. And we find 2 pi times root 3. Or sorry, 2 pi over root 3. Okay, so that's the value of that definite integral there. Cool. Okay, so another example. So we can do another example like that. Yeah, I think we'll move over here. So another example just to illustrate is the following integral. Okay, so it's so this integral from 0 to 2 pi of this function of theta here, and then we're dividing by 2 pi. You can think of that as like the average value of this function that we're integrating over the interval from 0 to 2 pi. Okay, and again, we'll proceed the same way as we did before. The key starting trick to be that we introduce complex numbers by replacing cosine theta with exponentials. So we have d theta over 1 minus 2a. Actually, take it back, because cosine theta involves a factor of 1/2, right? So we'll just kill that 2 right off the bat. And that's our definition of cosine making an appearance there. Okay. All right, so we find that. And again, that e to the minus I theta is 1 over e to the I theta. So we'll multiply by e to the I theta over e to the I theta in the top and the bottom. And what we find out is, let's see, so we have in the numerator we'll have e to the I theta d theta. In the denominator we have minus a e to the I theta squared. We have plus 1 plus a squared times e to the I theta, and then we have minus a. Right, if we just do some basic algebra. Okay, and I think, right, okay. So again, just as before, if we take z, so z of theta, so imagine this is the parametrized version of some line integral. So what we're going to make it is the line integral is going to be around the unit circle again. So we have z of theta is e to the I theta, theta between 0 and 2 pi. And so our dz d theta is I e to the I theta. And so as before, well, I'm going to want the I e to the I theta to show up. So I can insert that I that way, and that looks nice because the Cauchy integral formula involves that 1 over 2 pi I. So that's a very natural thing to show up. So we have our dz d theta. Let's see, so dz d theta, that's here, and that's our I e to the I theta, and our substitution z of theta, oh no, what was that? Substitution z of theta, that's these guys here. Okay, so what we find is we have 1 over 2 pi I, integral from 0 to 2 pi, or no, well, yeah, we're making this a complex line integral now, so this is just going to be around the unit circle, as we discussed. And our dz d theta, that's just corresponding to dz. So we're going to have dz on top. I'm going to take a minus sign from the denominator and just put it in the numerator. So I'm going to put a minus there, and then we'll have az squared plus 1 plus a squared z minus a. Okay, so again, we have this rational function of z, where we have just a constant numerator and a quadratic function in the denominator. So to do some scratch work here, again, we'll just factor this denominator. And this one's easy enough to do without the quadratic formula, so it's easy to guess a factorization here. So kind of natural guess is we have az and z, and then what else do we need? Well, we need this a squared here in the middle, so that's going to come from az times a. So let's see, so I think I need a plus a. I feel like Something's off here. Oh, I see what's off. Excuse me. Let me take care of something here. This plus sign should be a minus sign. And that's going to mean that plus sign is a minus sign because I took that factor of -1 out. Okay, so this should be a minus sign now. Oh, and this should be a plus sign. Good grief. Okay, so now I think I have my signs straight. Do I? Is that right? Yes. Okay. Sorry. Okay. So now, yeah. So we really need a minus a squared. So we have minus a squared z in the middle here. So I need a minus a here to pair with the that would be the outer terms in the FOIL, and then the inner terms in the FOIL, that would just, we would want that to be a minus z, so that's just going to be, we're going to need a -1 there, and that works with the plus a at the end there. Okay, so that's the factorization, and to apply Cauchy's integral formula, again, our contour, our curve is the unit circle. And here we'll make an assumption about A, which I probably should have stated at the outset. So our A here is a real number. We're dealing with a real integral at the start. And we'll assume that A is between 0 and 1, so that A falls in the interior of the unit circle. So our A would be something like that. Okay, so we're assuming that A is between 0, and 1. All right, so we return to our calculation. Right, there we go. And A, that's inside our contour, right? So that's going to be the thing we want in the denominator of Cauchy's formula. So we're just doing some cosmetics here. So we have -1 over, well, actually you can say, so -1 over AZ minus 1. That's the same thing as 1 over 1 minus AZ. So this is going to be our F. This is F of Z. And then we're dividing that by Z minus A. And we're integrating that with respect to Z. Okay. And so just a couple of things we have to verify. So our curve is going around this A here. Right, so gamma is going around A. So A is in the interior of gamma. So that's one thing we have to check. The other thing we have to check is that our F is holomorphic in the interior of our curve gamma that we're integrating around. And so the only problem point would be where this is a simple rational function, and the only problem would be where this denominator is undefined. And that only happens at Z is equal to 1 over A. Right, so F of Z is not holomorphic at Z equals 1 over A, but this is outside of gamma, right, since 1 over A is bigger than 1, right, which follows directly from the inequality that A is between 0 and 1. Okay, so our F of Z is holomorphic in that unit disk inside the unit circle, and so we can apply Cauchy's formula. So this is going to be from Cauchy's integral formula. We just take that F and we evaluate at A. And so we find that this is 1 over 1 minus a squared. Okay. All right, so this somewhat weird integral. Again, it's a bit similar to the previous one. If you take a look there, you have this trig function and then some other constants, but we just have this parameter a in this case. Okay, so you have these definite. So sometimes I guess definite trig integrals, if you have them over a full period, can be amenable to complex methods by just sort of assuming that the theta is going around the unit circle. It's sort of a natural thing to guess, or at least natural thing to try if you're stuck. All right. So that's applications of Cauchy's integral formula to real integrals. And we'll see more applications of complex variable methods to computing real integrals later when we talk about after we talk about the residue theorem, which is really, that was how, so Cauchy sort of discovered his residue theorem by trying to apply complex variable methods to computing real integrals. But we'll talk about that in the future. All right. Cauchy's theorem. So that was Cauchy's integral formula a couple of times. Cauchy's theorem basically says that if you're holomorphic on the interior of some typical closed curve, then that integral comes out to be 0. And you might think, well, can't be really many interesting applications of that. You're just computing that something is equal to 0. I mean, how interesting could that possibly be? What interesting examples? I give you a holomorphic function, you integrate it around a curve, you always get 0, so what? Well, turns out you can get some interesting information out of that. And so one interesting application would be to apply that to a function that it wouldn't be easy to integrate explicitly, right? So it might be interesting to say that the integral of a complex function f of z around some curve is equal to 0 if it's not clear a priori how you would evaluate that integral explicitly. So for example, so here's an example. We're going to consider, so basically we're going to consider the function f of z equals e to the minus z squared. So if we apply Cauchy's theorem around a rectangle, and so I have a rectangle like this in mind. So it'll be, so let me, so the curve will be like this. Okay, and this is R here, and this is I beta. And so any rectangle, so the dimensions are R by beta of this rectangle. And so you integrate f around that gamma, so call that gamma, and you get 0. Right, so okay, who cares? Well, it wouldn't be so easy to compute this integral from first principles because, I mean, how would you do it? You would parameterize around this curve, and then you'd be confronted with integrals involving e to the minus. So let's say you integrate along the just think about this one segment along the real axis, this first segment here. Now, your natural integral parameter would just be x, and so one of the integrals you'd have to do is e to the minus x squared, but it's not easy to integrate e to the minus x squared because it's actually known that there's no explicit antiderivative for e to the minus x squared. So integrating that from 0 to r is not something you could do explicitly. So there's sort of implicitly some information in here that would be difficult to get in any explicit manner. So we can dig into this a little bit more, so we can see what this is actually telling us in some detail if we expand this out. So let me see here. Okay, right. So this rectangle, let me see here. So let's call that first bit gamma 1, the second bit gamma 2, the third bit gamma 3, and the fourth bit gamma 4. So gamma 1, we can parameterize that. So we're just going to write down some parameterizations here. We can just use the parameterization t. So this is t, and t is going to go between 0 and r. Right, so gamma of t is equal to t. Maybe I'll be more precise about that. Gamma of t equals t, and t is between 0 and r. Gamma 2 of t, that's equal to, well, our curve, it starts at r, right, and then it goes up the imaginary, well, and then it increases purely vertically, right? So we add on some imaginary part, and that t, that imaginary part, is going between 0 and beta. Right, until we get up to that height of beta. Gamma 3, so let's see, gamma 3, well, we start at r plus I beta, and then we're subtracting off t, right? Just purely real stuff. We're moving purely in the horizontal direction, and we're subtracting off, right? So at 0, we haven't subtracted off anything, and then we continuously subtract off until we've subtracted off all of that horizontal component of size r. And then gamma 4 of t, we can say that starts at I beta, and then that subtracts off imaginary stuff, where the amount of that is between 0 and beta. Okay, so we write out some parameterizations. That's what we would get. And so explicitly here, we can write out what this Cauchy's theorem is telling us. So we'd have that this is the, right, so 0, it's the sum over all of these gamma i's, e to the minus z squared dz, I from 1 to 4. And so let's see, so that integral for gamma 1, that looks like integral from 0 to r of e to the minus t squared dt, because gamma 1 prime is just 1, so there's nothing interesting additional on that integral. Then we have the integral from 0 to beta of, so we have e to the minus z squared, so that's r plus it squared, and then dz dt here is just I, so we have an I and then a dt. The third one we have integral from 0 to r. We have e to the minus, so our z is r minus t plus I beta. And so I put the r and the t together because they're real, squared. And then the derivative, the dz dt there is a minus 1. So I guess I can, nope, that's the wrong thing. Minus. Okay, all that for minus sign. And the fourth one, we're going to have so we'll have an integral from 0 to beta. We have e to the minus z squared. And, well, we have the minus sign, but we have an I, a factor of I. And that squared, that's going to give us a minus 1. So actually we just have beta minus t squared dt. But wait a second. We have to do our dz dt, and that's negative I. So we have a negative I out front here. Okay. All right. So we have these four integrals sum up to give you 0. All right. Okay. So now to really extract real information out of this, real as in real numbers, we have to split things into real and imaginary parts. So let's write all this out. So the first one, that's purely real. So we have 0 to r e to the minus t squared dt. Let's see here. The next one, right. So, all right, so we're just simply sort of simplifying things here. So if we multiply things out, we have an I, we have an e to the minus r squared plus t squared. And then we have an e to the minus 2r I t. Okay, so we have e to the minus 2r times t times I. Right, so we're just foiling out that square in the exponential. And so that is just going to be some cosines and sines. So we're going to get cosine of 2r times t. The minus goes away because cosine is even, and then we have a minus I times sine of the same thing. And the minus comes out next to the sine because sine is odd. Okay, and then we have a minus integral from 0 to r of e to the minus r minus t squared plus beta squared. And then we have a very similar thing, except now instead of t we have now instead of t and r we have beta and r minus t. So we have cosine of 2 beta times r minus t, and we have sine of 2 beta times r minus t. And then we have minus I integral from 0 to beta e to the beta minus t squared dt. Okay, so now we can split into, so now this 0 is equal to this whole thing. So if we split into real and imaginary parts, that means the real part is 0 and the imaginary part is 0. So if we write that out, what we find is, right, so, okay, all right, so let's do this. So the real part, okay, so integral from 0 to r of e to the minus t squared dt, right, that's real. From the second term, a real part is, we get a plus integral from 0 to beta of, oh yeah, let me try to simplify this. So I can pull out an e to the minus r squared. That's just a constant. Integral 0 to beta, e to the t squared times sine of 2rt dt. Right, that's real. And that's we get the e, the I and the minus I times in the sign. Those come together, and then you have something real. And then in the next one, the third term there, the real stuff comes from this part, 0 to r. Again, I'm going to pull the e to the beta squared out, and then we have integral from 0 to r, e to the minus r minus t squared cosine of 2 beta times r minus t dt. Okay, so that equals 0, and then something else equals 0. The imaginary part equals 0 as well. So what we find is, we're dropping the i's. So we get integral from 0 to beta. Whoops. God, I keep doing this. E to the minus r squared. Integral from 0 to beta, e to the t squared, cosine of 2rt dt. Then we have minus integral from 0 to r of, oh my god, minus e to the beta squared, pulling that out, integral from 0 to r, e to the minus r minus t squared times sine. Oh, actually it looks like we have double negatives. It looks like this is going to be a plus sign here. Right, because that sine has a minus there in that integral. Sine of 2 beta r minus t dt. And then we have minus integral from 0 to beta of e to the beta minus t squared dt. Okay. So these are the two things we're looking at here. These two lines, last two lines. So that's the real information that's contained in the fact that integral around that rectangle of e to the minus z squared dz is equal to 0. Okay, so now one thing we can use here is, so here's a little just calculus fact. That the integral from 0 to a of, let's say we have some continuous function h, and we're looking at a minus x dx. So we're integrating h of a minus x dx from 0 to a. And that's the same thing as the integral from 0 to a of h of x. which you can just check with a U substitution, or you can think about it geometrically, convince yourself with that just geometrically, that they're just computing the same area. And we're going to use that in this integral here, right? So we have this r minus t. So let me maybe mark them in red. So I got this r minus t, right, from 0 to r. And I have this r minus t and r minus t from 0 to r. And I have beta minus t from 0 to beta. So I can just change those r minus t's to just t and beta minus t to just t as well by this little fact. And so we can rewrite this information as, so are these two lines here, we can rewrite this as integral from 0 to r e to the minus t squared dt plus e to the minus r squared integral from 0 to beta e to the t squared sine of 2rt dt. That's equal to e to the beta squared integral from 0 to r of e to the minus r minus t. I can just replace that with t, and same inside the cosine, so we got cosine of 2 beta t. It's a little less complicated. And we also have, in rearranging that second line, 0 to beta e to the t squared dt. So that's taking this last term here with the minus, putting it on the other side, and replacing beta minus t with t by that little calculus fact. And then that's equal to e to the minus r squared integral 0 to beta t squared cosine 2rt dt plus e to the beta squared integral from 0 to r of e to the minus t squared sine of 2 beta t dt. Okay, so we get these rather baroque looking integral identities out of the very simple fact that, right, the seemingly trivial fact that, well, we just sort of pick this random holomorphic function and the integral around a rectangle of it has to be equal to 0. So we derive these integral identities here, which definitely don't look very obvious. If somebody presented you the identities and told you to derive them, they certainly wouldn't look very obvious. Okay, and well, on the other hand, it might not look like they're good for very much, and I don't have a great application for them, but they certainly, I don't know, they certainly have a kind of aesthetic appeal to them. And there's a simpler set of formulas that we can deduce from these if we take a certain limit. So let me just box these in yellow here because they're important. All right. So now what we're going to do is we're going to take the limit as r goes to infinity. Okay, so basically, well, yeah, so you kind of think you're taking that rectangle and letting the right hand vertical edge of it disappear off to infinity. Okay, so if we do that, so first of all, okay, so the first thing to notice is that these two terms here, let's see, so these, yeah, am I thinking about this right? Yes, right, so these terms in green, they both go to 0. Okay, so green boxes green box terms go to 0. And why is that? Well, let's see. So I'll just look at the first one. The other one is almost exactly the same, and you'll be able to see that clearly. So that first one, right? Well, that's this this quotient here, and this first integral. Well, we can estimate how big this is, right? So basically claim that this numerator here in this quotient is under control. It's bounded no matter what r is, and clearly this denominator is getting extremely large as r goes to infinity, right? So if that numerator is bounded, then this thing is going to get dragged to 0. So if I look at the absolute value of this quantity, well, we know that absolute value, just from calculus, right, the absolute value of this integral it's computing in area, that's no worse than the integral of the absolute value, right? So that would be e to the t squared absolute value sine 2rt dt over e to the r squared. And sine is always bounded in absolute value by 1. All right, so this is just the integral from 0 to beta of e to the t squared dt over e to the r squared. All right, and so this is the point at which you can realize the proof is the same for the other green box integral, because sine and cosine have the same property that they're bounded by 1. And notice that this numerator is independent of r. Right, so this quantity here goes to 0 as r goes to infinity. Right, so both of those terms are going to drop out, and we get the following identities. So give myself just a little bit more room here. So we get the integral from 0 to infinity of e to the minus t squared dt is equal to e to the beta squared integral from 0 to infinity of e to the minus t squared cosine 2 beta t dt. And we get integral from 0 to beta e to the t squared dt is equal to e to the beta squared integral from 0 to infinity of e to the minus t squared sine of 2 beta t dt. Okay, so we get these much simpler identities that only involve this single parameter beta, which have a, again, kind of nice aesthetic appeal, and certainly would be, or not so obvious how you would derive these just if you didn't know about complex numbers and Cauchy's theorem. And one more simplification is actually, so this integral here, we can compute this integral. So this is a rather famous integral that you can compute. So integral from 0 to infinity of e to the minus t squared dt. So I can show you how to compute this integral. First of all, since e to the minus t squared is an even function, this is 1/2 the integral from negative infinity to infinity of e to the minus t squared. And I'll just change t to x because I feel like it. Okay, and I'll show you how to compute this integral in negative infinity to infinity of e to the minus x squared dx. So the standard trick for this, for computing this integral, is that you square it. So one way to write that is you use a different variable name for the other one. Let's say we use y. And now we can think about this as a double integral. Whoops, I lost the other one. Right, it's just a double integral. Like if you took this double integral and you're integrating over x on the inside first, you can pull that e to the minus y squared out because that's just a constant with respect to x, and you just have the then you just have this integral on the inside, right? But then that's just a number, and you can pull that out, and then you have the integral of the y stuff left, right? So you can see how writing this integral as an iterated integral, you get that this equality. And then the fun little trick here is that this integral, so this is just an integral over R2, so let's just say this is an integral over R2 of e to the minus x, let's say e to the minus x squared plus y squared, dx dy. But now this is amenable to polar coordinates. So now I can say that this is an integral over r squared. Well, maybe I shouldn't say that. Well, so this is a double integral. So we have e to the minus r squared r dr d theta. And our r goes from 0 to infinity, and our theta goes from 0 to 2 pi, right? Because that parameterizes the entire plane. And this integral is very doable. So the theta integral, you just get 2 pi, and the r integral, negative r squared's integral, negative r squared's derivative is negative 2r. So if I sort of insert a minus 2r in here, right, and put a minus 1/2 out here, then let me see here. Then I can give myself then I have myself a minus 1 there, right? And then my antiderivative of e to the minus r squared times negative 2r is just e to the minus r squared, and I'm evaluating that from 0 to infinity. And so this becomes negative pi times, we have a limit of, let's say, big R, as big R goes to infinity, of e to the minus big R squared minus e to the 0, which is just 1. And so this is pi times limit as big R goes to infinity of 1 minus e to the minus r squared. And e to the minus r squared, that goes to 0 as r goes to infinity. So this is just pi. Okay, so the square of right, so this integral, let me just emphasize, so this integral here, its square is equal to pi, right? So that means that the integral itself, that guy in red, is equal to the square root of pi. Right? So if we go back up here, this is the square root of pi over 2. Because remember, the original integral we were interested in is just the integral from 0 to infinity. So if we return back up to here, this first equation, that's equivalent to square root of pi over 2 is equal to e to the beta squared integral from 0 to infinity of e to the minus t squared cosine 2 beta t dt. Right. So we also have these two identities here. Right. So not only is square root of pi over 2 equal to this integral from 0 to infinity of e to the minus t squared, square root of pi over 2 is also equal to the integral from 0 to infinity of e to the minus t squared times cosine of 2 beta t. And then if you adjust that by e to the b squared, or sorry, e to the beta squared, that still also comes out to square root of pi over 2. So kind of interesting there. And if instead you multiply that e to the minus t squared times sine of 2 beta t, and then you adjust by e to the beta squared outside, that is not an explicit constant. It's not an explicit constant, but what it is this integral here. This is really the antiderivative of, so if you set f of beta equal to integral from 0 to beta e to the t squared dt, then f prime of beta, that's equal to e to the beta squared. So this definite integral is an antiderivative for e to the beta squared. So we don't, there's not a good closed form simple antiderivative for this function e to the beta squared in terms of elementary functions like sines and cosines and familiar things like that. So the best we can do is use the fundamental theorem of calculus to write down an antiderivative, but this one identity we've derived gives some information about that antiderivative. It gives you this alternate formula for that antiderivative. All right, so that's one way to look at or think about this second integral formula, and this other one is just this interesting integral identity involving pi. Okay, anyway, so this is just some of the things you can do with Cauchy's integral theorem and Cauchy's formula. All right, I think that's all I have to say for now, so I'll cut it off here.